Point of emphasis that we want to make in terms of any type of investment, whether it be a project for a firm or an individual security, is that we have an interest in both expected returns and in risk. And to try to temper between those two, we want to try to illustrate one of the key things that you'd be looking for in terms of putting together a portfolio and how you may benefit by diversification. And we'll make reference to correlation in that process. So this problem shows, first of all, how do you calculate correlation? How is it related to the other summary measures that you might have? And secondly, wants to take a look at the notion of creating a portfolio and why you benefit from diversification. So here you've decided to create a portfolio that includes only two assets, Mars Incorporated common stock and JVC common stock. Before making the investment, you'd like to be able to determine the risk and return trade-offs between these two as you create a portfolio. Given the following return information that's provided in here for each of these, what we want to be able to do is to determine the correlation between these two stocks and then look at what the efficient frontier would look like. Here we've done it for just 10% weighted differences in each of these and seeing what that tells us about the return and the risk of the portfolio overall. So the first thing we want to begin with is to take a look at some of the summary measures. Unlike the probability distributions that you've seen in prior problems, what we've got here are just 10 observations that we're going to use to sample to try to tell us a little bit about the properties of the overall distribution. So instead we're going to be looking at relative frequencies in here. Now, first thing we want to find is what is the expected return or the mean. We're going to go to the function wizard, and under the statistical function, so if you pull up the menu for statistical, we're looking for the function that tells us about the mean, and that function is called average. It's providing the arithmetic mean. So we're going to tell that OK. And what we want to do here is to highlight the data for Mars in terms of its rates of return. And these are in the cells B8 through B17, and you can see here it's going to give us a return of 16.2%. Okay, well that's fine. There's the starting point there. Likewise, we want to do the same thing for JVC, so I can just copy and paste that expression in place here. And we see JVC has a higher expected return of 16.3%. Now the question becomes, how do they look with respect to risk? And here, again, we're dealing with a individual observation, so we can go back to our statistical function to be able to take a look at that. And as you do, we're looking for a function called standard deviation. And as you work your way down here, you can see that there are a number of things that are presented here under standard deviation. But the first of these is the one we want, STDEV, which is talking about a sampling of information, and we'll calculate the estimate here for a sample. So we'll tell that OK, and we want to highlight the data here for Mars. And we can see that it has a value of 0.020976. Or 2.1. Now that's not a percentage as we've shown previously. So let's go ahead and change that format. I'm sorry, that is a percentage with the formatting we're going to want for variance, which is nothing more than this squared. So if I square that standard deviation, this is not a percentage, and this one we do want to be able to change to the formatting to just represent a number. So let's look at that as a straight number. And you come through here, and there's the value for the variance. I can again copy and paste these, and what we'll observe is that the much higher variability that we observe there in the returns for JVC, expect to find a higher standard deviation and higher variance to be able to reflect it. So when we paste that in there, indeed we do. You can see that the standard deviation is significantly higher. Okay, now those are the base summary measures that we've seen previously. The next measure that we want to look at is a measure called correlation. And correlation is asking for the strength of the linear relationship between two variables, in this case Mars and JVC. So what we want to know is when you go from one period to the next, how do they move together? So you can see Mars goes down from 18 to 14, JVC goes down from 19 to 12. Mars goes down from 14 to 13, but JVC jumps up. Mars goes up, JVC jumps down. Mars goes up some more, JVC jumps down even more. So you can see they're not really working hand in hand. The correlation measure, if you recall, is somewhere between a -1 and a +1. So the strength of it here, +1 would be if they move positively together in a linear fashion. A negative one would be if they work perfectly in a negative, one goes up, the other goes down, and vice versa. Here it's mixed, so we're expecting a correlation that's probably going to be somewhere closer to a 0 value than it is certainly either of the extremes. Now, the measure itself is given in here. Going to the statistical functions under the function wizard, we're looking for the function that represents correlation, and here it is, CORREL, which just says let's take this data and find out how they're correlated. So the first array would be the returns that we observe here for Mars. The second array would be the returns that we observe for JVC. And you can see we're going to get a number of just 0.109, which, as we expected, is much closer to 0 than it was to either of the other extremes. So that's how those two things are correlated. Now, one other measure that we do want to be able to use in here is something called the covariance. And what it wants to do, much like the variance, it says, how do these things compare to their mean? And we squared that. Well, in the covariance, it asks in any particular period, how does each one of these compare to their respective mean? And you'll find in some cases, and this is the great benefit from diversification, is the fact that there are some periods where one observation is above the mean, but the other one is going to be below its mean. So if you look in here, for example, in period 8, 18% is a positive difference above this mean of 60.2, but the 12% is below. So the combined effect is a negative. So when we go ahead and look at that covariance, it's nothing more than the correlation coefficient that we would have times the standard deviation of one times the standard deviation of the other. And you get a covariance term in here that is fairly small relative to each of these variance figures. And that's where we're going to benefit from diversification. Now, we can create the portfolio and see what's going on with the portfolio. Now, if we have 0 weight in Mars, the remaining 100% is going to be the weight that goes into JVC. So if we had nothing in Mars, we would expect to just, if we're only holding JVC, to get both the mean and the standard deviation of JVC resulting through here. Likewise, if we only held 100% of Mars, then we would expect on average to get the average Mars return. And that's what we're going to see here with respect to the portfolio. Now, what the portfolio return is, it's the sum of the weights times the rates of return that's expected for each case here. So let's begin here by taking the weight on Mars and multiplying that by the expected return on Mars. To that, we're going to add the weight that we would have on JVC, which is just 1 minus this information that we had in cell E8, okay, multiplied by the expected return on JVC. So this is what we mean by an expected return for the portfolio, the sum of the weights times the rates. Now, our weights are going to go from line to line. They'll pick up the 10, the 20, the 30, and so on. So that's fine. But the expected returns, the means, are the same every time. So we're going to lock these in terms of line 18 information so that we're going to be able to copy this as we go down from cell to cell. So I'll put that $sign there, and you can see with a 0% weight on Mars, we expect the 16.3% to result, and it does. Likewise, if we had 100%, so we just copy this, if I paste it down here where it's 100% Mars, I expect to see this 16.2%. And indeed, I do. Now, in between, what you're going to find is, as your portfolio has a higher percentage weight in Mars, it begins to approach more of the effect of Mars. And it's going to move in a linear fashion. So when I paste this in here, you can see every 10% increase in Mars is a 100% decrease in the return on the portfolio. So it keeps working down this nice linear fashion to go between the extremes of 16.3% and 16.2. So that's what happens with diversification. Okay? just a linear combination here on the returns for the portfolio. The risk of the portfolio, however, is dramatically different. While we will have with 100% in JVC, we're going to find that the standard deviation of the portfolio is just this value that we would have here of 7.47%. And at 100% in Mars, we're going to find this extreme of 2.1%. We won't get the same regular movement that happens in between. And this is why diversification works. So let's go ahead and let's put in what's going to happen in the case of the standard deviation of the portfolio and how it relates to all of these measures. First of all, we begin here by what is the weight that we're going to have on Mars. And we're going to square that, okay, because what we're going to look for here first, and I'm going to put this whole thing in parentheses here, is we're going to look for the variance. The standard deviation is just going to be the square root of that. So we're going to invoke the SQRT function here once we figure out what's going to go on here at the end. Now, we're going to take the squared weight on the portfolio of Mars, and we want to multiply that weight times the variance that we would have for Mars. Okay, now, each time, we're going to again lock this in on that, so I'll put a $sign in there to pick up that same variance. To this, we're going to add the effect that JVC adds all by itself, and that is going to be the weight on JVC, which is 1 minus the weight on Mars. Okay, and we're going to square that one as well. Okay, and that squared weight is going to be multiplied by the variance that we have for JVC. So again, I'm going to use that same variance every time, so let me go ahead and put a $sign in to be able to fix that. Now, that's the individual components. So you've got the weight on each of the individual components. Now we want to find out what does their combination do. And we'll have cross terms, and we'll have Mars and how it affects JVC, and JVC and how it affects Mars. So this will be 2 times, and what we'll have here would be the weight on Mars, which was in cell E8, times the weight on JVC, which is 1 minus what fits there in cell E8. Okay, so I've got 2 times the weight on Mars times the weight on JVC, and all of this is going to be multiplied by the covariance, okay, the number we just calculated down here, for the portfolio. And again, it's the same covariance each time, so I'll put a $sign in there in order to fix that in line 22. And what you get here is a combination of all of these things. This information inside the square root symbol, that's the variance. When I take the square root, I get the standard deviation. So just as we said, if you are 100% JVC and 0% Mars, your portfolio takes on the standard deviation here for JVC. If I copy that and paste that place down here, when I'm 100% in Mars, I'm going to have the characteristics involved for Mars. But look at what happens in between. If I paste these in place, you can see that it's not the same kind of regular movement that we have going on. And in fact, there was no effect of an increased risk when I took it from 100% Mars down to 90%. I see that these movements are slowly working their way towards the other extreme, all the way up here on that portfolio. And this is how you benefit by diversification, is you try to find the mixture in here for the portfolio that provides this nice regular trade-off in terms of expected return, but take advantage of this irregular trade-off that you're going to have with respect to risk. Now, we can see that by looking at the portfolio mapped out. And if you take a look at the risk and the return of the portfolio and use your graphing tool, what you're going to find is you get this notion of the efficient frontier. And it is not a straight line between the two. Okay, so here are the endpoints. These endpoints at 16.2% and 2.1% risk, this is putting 100% of it in Mars. Up here at 16.3% and 7.47% for the risk, this is putting 100% in terms of JVC. And it's not a linear trade-off. It's not a straight line in between these 2 points that you're coming up with. Instead, we get some benefit by diversification. And since we want to be to lower risk down this way and to higher return, depending on the nature of where your indifference curves fit through, that's going to tell you some optimal portfolio where you can take the greatest advantage of diversification. But this is how that would work in terms of its overall calculation.